Cities, forests, oceans, people. Everything in the universe is made from matter created in the first seconds of the Big Bang. Every star, every planet, every atom, every blade of grass, every drop of water.
Water is ancient. The hydrogen atoms in here were born moments after the Big Bang. Then came everything else.
The Big Bang is the defining event of our universe and everything in it. The secrets of our past, our present, and our future are locked inside this one moment in time. To unlock the secrets of the Big Bang, we have to travel outside of our own solar system and journey beyond even our own galaxy. As we travel into deep space, we're actually seeing into the past and getting closer to being able to witness the dawn of time itself. Passing the first infant galaxies and the first stars. We arrive back at the moment the universe began and face the biggest questions in all of science.
This is the holy grail of physics. We want to know why it banged. We want to know what banged. We want to know what was there before the bang.
To get the answers, we've built machines the size of cities to simulate conditions when the universe was created, and space telescopes to peer deep into our past.
We are getting close to answering the old 8 questions. Why are we here? Where did we come from? Does the universe, in fact, have a beginning or an end? And if so, what are they like? If we find the answer to that, it would be the ultimate triumph of human reason. We would know the mind of God.
The origin of the Big Bang is the greatest mystery of all time. And the more we learn, the deeper the mystery becomes.
We like to think that our universe is unique. However, now we're not so sure. Perhaps there is a multiverse of universes.
Another possibility is that our Big Bang is just one of many Big Bangs, but it may be one of just an infinite number of universes, and there may be other regions in that infinite number of universes where a Big Bang is just happening today.
But there's only one universe we're sure of, and understanding this one is hard enough. Since the late 1920s, everything we know about how our universe works has been turned upside down.
It's important to realize how much our picture of the universe has changed in the last century. At the beginning of the 20th century, the conventional wisdom in science was that the universe was static and eternal.
In 1929, that all changed. At the Mount Wilson Observatory above Los Angeles, astronomer Edwin Hubble discovered galaxies aren't stuck in one place. Not only are they moving, but they're flying away from Earth at incredible speeds. This was the first real evidence of the Big Bang.
All galaxies on average were moving away from us, and stranger still, those that were twice as far away were moving twice as fast. And those that were 3 times as far away were moving 3 times as fast, and so on. Everything was moving away from us.
It became known as Hubble's Law. His discovery is still the starting point for exploration of the Big Bang.
What Hubble convincingly demonstrated by seeing the motion of those galaxies is that the universe is expanding.
Theoretically, an expanding universe must have started from a single point. By measuring how fast the universe is expanding, astronomers calculated backwards and figured out when it burst into life.
People ask the question, how do you know that the universe is 13.7 billion years old? I mean, smarty pants, you weren't there 13.7 billion years ago. Well, when you watch television on videotape, you hit the stop button when you see an explosion, and you could run it backwards and see when it actually took place. The same thing takes place with cosmology. We can run the videotape backwards and then calculate when it all came from a cosmic explosion.
You don't have to be an astronomer to look back in time. If you gaze up at the night sky, you're seeing stars that are millions of light years away, meaning it took the light from those stars millions of years to get here. So, if you look far enough, you should be able to see the beginning of the universe. Named for the groundbreaking astronomer, the Hubble Space Telescope allows us to look deep into the universe, back in time, and closer to the moment of the Big Bang. But for scientists, winding back the clock to the Big Bang was only the first step.
When people first hear about the Big Bang Theory, they say, well, where did it take place? It took place over there, it took place over there. Where did it take place? Actually, it took place everywhere, because the universe itself was extremely small at that time.
These are only some of the most abstract and difficult concepts there are. So here's a mind bender. What came before the Big Bang?
The philosophers in ancient times used to say, how could something arise from nothing? And what's amazing to me is that the laws of physics allow that to happen. And it means that our whole universe, everything we see, everything that matters to us today, could have arisen out of precisely nothing.
It's one of the biggest hurdles to understanding the Big Bang. First, you have to buy into the premise that something was created out of nothing.
It's impossible to describe the moment of creation in human language. All we know is that from what may have been nothing, we go to a state of almost infinite density and infinite temperature and infinite violence.
Understanding how nothing turned into something may be the greatest mystery of our universe. But if you understand that, you start to understand the Big Bang, when time and space began, and a great big explosion created everything.
It's 100,000 years since our solar system formed. The young Earth already looks like a planet. It's round. It has an iron core and a rocky surface. Yet our baby planet is just a few hundred miles across. It has a long way to go. It must grow 4,000 times more massive. And it has competition. Thousands of other protoplanets shoot through the solar system, often colliding at over 20,000 miles per hour. You can find proof of this ancient destructive era in modern-day Arizona. Not Meteor Crater itself, that's just 50,000 years old, but the asteroid that gouged it out. That was 4.5 billion years old. Mark Sykes and Marvin Kilgore think the asteroid came from a violent event in the early solar system. The asteroid flew through space for billions of years. Then it hit Earth. They aimed to find a fragment of the asteroid, a remnant from the period of planetary formation.
About 6 miles from here is Meteor Crater, and that was a impact 50,000 years or so ago, and it spewed a bunch of pieces out.
They're convinced the original asteroid was rich in iron, so they've come prepared with some impressive metal detectors.
Does it work?
Oh yeah.
That's the sound we're listening for.
But even with a quad-drawn metal detector, meteorites are hard to find.
Yeah, are you pretty convinced there's nothing there?
I don't really, not detecting anything.
They find metal, but no meteorites.
My great discovery of the afternoon has been this bolt and this piece of wire.
It takes hours of searching and many false alarms. Then, with the light fading, the detector sounds again.
How about that? Success at last.
This meteorite is over 90% iron and nickel. It could only form right in the core of a protoplanet. The protoplanet it came from must have smashed apart in a brutal collision.
Well, in the early solar system, it was a pretty violent place, and these protoplanetary embryos would smash into each other, and they would shatter each other, exposing the interior cores like this. It was a very tumultuous time.
Entire worlds reduced to chunks of rock and metal and scattered into outer space. In the early solar system, these vast collisions are common. The young Earth is in danger. The period's name is the Titanomachian, literally, the War of the Titans. All rocky planets, the Earth included, go through this destructive phase. Sometimes they shatter completely. Sometimes one consumes the other.
All the big guys are sort of competing with one another in a very violent way, actually, to see who comes out on top by eating all their neighbors.
The battle lasts over 30 million years. Finally, thousands of protoplanets have combined into a few full-size planets. Mercury, Venus, Earth, Mars, and a fifth planet, Theia. It's racing toward Earth, our planet's last giant impact. Theia is the size of Mars, big enough to destroy the Earth.
If that thing had hit us straight on, it could have literally blown the Earth to bits, and then we wouldn't even have a planet today.
If this Mars-like object had a direct hit with the Earth, perhaps there would have been another asteroid belt where the Earth is today.
But Earth is in luck. Instead of a head-on crash, Theia strikes a glancing blow. It's the most violent event the Earth has ever known. The impact turns the Earth back to a molten world. A vast magma ocean 600 miles deep. The Earth barely survives. And the encounter changes our world forever. Material blasts out into space. Enough rock to build a mountain as wide as America and 10,000 miles high.
It would have been so much energy, so much catastrophe. Huge amounts of material blasted off and went into orbit around the Earth.
The debris forms a huge ring around the Earth. This gathers together to form two rocky bodies, both orbiting the Earth.
Something the size of Mars hit the Earth about 4 billion years ago. Lots of material would have been thrown off. We now think that it may have formed not only one moon, but two.
For millions of years, two moons dominate the Earth's sky. Eventually, they drift together and collide. Two moons merge into one. The massive moon we see today.
There's no other planet that we know of that has a moon as large as ours in comparison to the size of the planet. We're almost a binary planet, two worlds going around each other.
Without this large moon, we might not even be here. The moon keeps the Earth spinning at the same angle. That steadies our climate.
The fact that the Earth's axis stays in the same direction as it goes around the sun produces the seasons, but regular seasons, things that life can depend upon as it evolves.
Earth is neither too hot nor too cold for life, thanks to our distance from the sun and our massive moon. The Earth is not covered in ice or steam, but in liquid water. Yet that water must come from somewhere. The newly formed Earth is dry. To get water, our planet must once again face disaster.
The Big Bang. No space. Total darkness. Nothing. Suddenly, the universe sparks into life. Really? Surely everyone knows. You can't get something from nothing.
It's really the ultimate question. How did the universe come into being? And the thing is, we don't want just everything to come from nothing. It seems like a trick. But here we are, we exist, so something must have happened, and we just don't understand the physics of it yet.
This is one of the big open questions in cosmology, the origin of the universe. And I think that people have variously said stuff like, oh, the universe has come from nothing.
Like, ta-da, now there's a universe. But remember, we don't have data about the earliest moments of the universe. We don't know what was going on.
We're struggling in the dark. To get insight into what may have happened before the Big Bang, that period of apparent nothingness, physicists look to empty space. But does empty really mean there's absolutely nothing there?
It's not that there's something coming from nothing, because that old-fashioned idea of nothing just doesn't apply to what we think of as empty space.
It turns out, empty space is far from empty. The vacuum of space is really a writhing sea, awash with charged quantum particles and electromagnetic fields.
The vacuum of space itself can be a very dynamic thing. Matter can spontaneously appear out of the vacuum and then spontaneously annihilate.
The vacuum is full of particles and antiparticles that are whizzing into existence and then disappearing, colliding with each other.
Space is full of virtual particles, popping in and out of existence.
And there's no question that they're real. Their effects are absolutely visible. We can see them.
In extreme physics, things can get strange. Maybe nothing is something after all. If empty space contains particles that apparently come from nothing, could some sort of similar process have triggered the Big Bang?
The quantum vacuum itself can randomly, spontaneously, without any input, just have a lot of energy. Perhaps enough energy to spark something that we would call a Big Bang.
There are many speculative theories about the origin of the universe. But is its sudden appearance out of nothingness the only trick it pulled off? It also made matter from energy. The universe is full of galaxies, stars, planets, and comets. Where did they all come from? According to the Big Bang narrative, from one tiny dot.
When the universe began, there was actually no room for matter at all. The temperature was so high, the spaces were so compressed that matter couldn't exist.
So how did the universe manage to become full of matter? In the primeval atom, there was no room for matter, but it was crammed full of energy. And as Einstein tells us, all we need to create matter is energy. According to E equals mc squared, energy and matter are interchangeable.
Einstein taught us, with special relativity, that energy and matter are two sides of the same coin. You can convert matter into energy by, say, blowing something up.
The most fearsome example of converting matter into energy was the atomic bomb, developed in the 1940s. But with the Big Bang, this process was reversed. Energy created matter. Matter that expanded out and out to fill a whole universe. And in cosmic terms, the universe, where matter would develop, grew remarkably fast.
Right after the universe was born, it had an unbelievable growth spurt, basically going from being a toddler to a teenager in the single tick of a clock.
How could the universe get so big so quickly? If we believe the Big Bang story, it appears to have broken one of the most fundamental laws of physics. Did the early universe really grow faster than the speed of light? In the classic Big Bang story, the observable universe expands from a ball of energy smaller than an atom. Today, the universe is estimated to be 93 billion light years in diameter.
Think about the vast universe that we see all around us today, and it was once a tiny, tiny little volume, unimaginably dense. The universe must have gone through a colossal growth spurt.
With a steady rate of expansion, there simply hasn't been enough time for the universe to grow to its current size. Regions of the universe that were close neighbors in the past are now so far apart that their separation can't be explained by normal expansion. And the huge size of the cosmos is not the only strange thing we've discovered. The universe is what astronomers call flat.
Our universe is lumpy and bumpy at small scales. There's galaxies, there's black holes, there's people, there's all sorts of junk. But at large scales, global scales, truly universal scales, our universe is flat.
Could this universal flatness and the super rapid growth somehow be connected? We know that the Big Bang wasn't an explosion, or matter in the universe would be unevenly distributed. Yet something pushed everything outwards and fast. But what? In 1980, Alan Guth, a young Stanford cosmologist, came up with a potential answer. His theory of inflation says the observable universe expanded from being smaller than an atom to the size of a basketball almost instantaneously.
In this tiny fraction of a second at the beginning of the universe, like a millionth of a second, but a millionth of that, a millionth of that, and a millionth of that, the universe expanded by, take the size of the universe at that time and multiply it by a 1 with, say, roughly 50 zeros behind it.
Inflation drove the accelerated expansion of the universe, made it get really, really big, really, really fast, and then it stopped.
Inflation seems to solve two Big Bang headaches: how the universe got so huge so quickly, and why it's so flat. Because it inflated everywhere at once, all the energy in the universe which would turn into matter was pushed out evenly at the same time and same pace.
And the first stars grow together to become the first galaxies. Even here, us in the solar system, we're born, we're seeded in the event of inflation.
The end of the universe is coming, but how will it play out? For a time, a big crunch was the likely answer. Dark matter, the invisible bulk of the universe, causes space to fall in on itself. Galaxies collide. Planet merges with planet. Everything becomes hotter and hotter, denser and denser.
The universe is like one giant star.
Dark energy kills the Big Crunch theory. It acts like rocket fuel for the expansion of space between galaxies.
They're not just coasting, they're getting pushed outward.
Only two possible fates remain, a big rip or a big freeze. Both scenarios rely on dark energy. For the universe to be torn to shreds in a big rip, dark energy must increase exponentially in the future. A big freeze requires a steady increase in dark energy, pushing galaxies apart.
We can't write the last chapter of our universe until we understand the nature of dark energy.
May 2009. The European Space Agency launches the Planck satellite to search for the birth of dark energy. Its ultra-sensitive telescope peers through space and time, back through billions of years, toward the beginning of everything, to capture this. This is our universe as it appeared 13.5 billion years ago, just 380,000 years after the Big Bang.
So what Planck has done is take a picture of the early universe and told us about what the early universe is like, and given us our most detailed and accurate picture of that moment in time.
The universe in this picture is a hot soup of protons, electrons, and photons. Hydrogen atoms have just started to form, and it's the light from this genesis of matter that we see here. Blue areas are colder, reds are warmer.
Eventually, those hot spots, those red spots you see in the map, are going to form large superclusters made up of hundreds or thousands of galaxies. Each one of those galaxies will contain billions of stars.
Gravity and expansion alone appear to drive the formation of these embryonic galaxies. Dark energy doesn't seem to have switched on yet. So when did dark energy take control of the universe? Astronomer Brenda Fry is part of a team using massive ground-based telescopes like this one at Kitt Peak, Arizona. She peers back in time to capture the universe through its childhood, as it was growing.
Right, so this is an aluminum plate. And into this plate are drilled 640 individual holes. Each one is put at a very specific place on the mask, which will correspond to one particular galaxy on the sky.
During each observation run, The light from 640 individual galaxies is collected using fiber optic cables. The speed and relative position of each galaxy is measured to pinpoint exactly where it is in space. So far, the team has accurately mapped around 1 million galaxies in 3D, and this is what they look like. Each one of these fuzzy patches is a fully grown galaxy containing around 200 billion stars.
This is a very basic measurement, and we think that this will be able to help us to get a grasp into the nature of dark energy.
Scientists compare this adolescent universe to its baby pictures. It shows dark energy emerging when the universe is half as old as it is today.
About 8 billion years after the Big Bang, this expansion of the universe begins to accelerate, and we're in the middle of this acceleration.
The data also shows that as space expands, dark energy increases in lockstep with it.
If you had a box and you put some dark energy in it, and then you went and you weighed that box. Now you take the box, you make it twice as big. You don't open it, you don't put anything in it, you weigh it again. It's going to weigh twice as much.
This remarkable observation means we should be safe from a big rip. Dark energy will continue to increase gradually. The universe is heading for a big freeze. Scientists can finally calculate a timeline for the end of the universe. It now seems that we live in an almost perfect universe with just enough gravity to hold the galaxies together and just enough dark energy that it will expand forever without ripping itself to shreds. Cosmologists can now finally envision the end of everything.
30 years ago, it was debatable, but now it appears that the universe most likely will suffer a deep freeze.
If you look at the data, it stares out at you.
In a big freeze, dark energy pushes galaxies further and further apart, but they remain intact. The stars inside them fade away.
Every star you see in the sky, including our sun, is burning through its nuclear fuel.
The gas will run out, stars will stop being made, and the ones that exist are it. Those are the last ones.
100 trillion years from now, the biggest stars will be the first to go extinct. Big stars burn bright and die hard. The star's core collapses, unleashing a supernova. Then gravity crushes the dead star down to a single dense spot. The bright star is now a black hole. Medium-sized stars like our sun will go next. As its supply of hydrogen runs out, it swells to a bloated fireball over 200 times its current size. In a violent universe, against all the odds, life survives. But consider this. At any moment, the universe could pull the trigger on a secret deep space death ray, obliterating all life on Earth. And until the 1960s, nobody knew it existed. 1967, the height of the Cold War. The United States and Soviet Union raced to outgun each other, stockpiling and testing nuclear weapons.
America was worried that the Soviet Union would be able to test nuclear weapons in space. So what America did is launched a series of satellites to go out into space and look for the telltale flash of gamma rays from nuclear tests.
On July 2nd, 1967, the satellites detect a burst of gamma rays, the most energetic and destructive form of electromagnetic radiation.
Immediately there was panic in the Pentagon. Perhaps the Russians are testing super gigantic hydrogen bombs in outer space, and we're just caught flat-footed.
But it's not bombs. It's something even deadlier.
And then the realization sunk in. Oh my God, These flashes are coming from outside the Milky Way galaxy. They must be billions of light years away. A new source of energy, second only to the Big Bang itself, had been discovered.
When gamma ray bursts were first discovered, people assumed that they must be fairly close by. Of course they have to be close by. They're the brightest thing that we see in the sky. And now we know that gamma ray bursts, not only are they not nearby, they're not in our galaxy, they're not in nearby galaxies, but they're close to the edge of the universe. They're as far away as anything else that we observe. And that's completely ridiculous.
Light gets dimmer over distance, so the further it's got to travel, the dimmer the light should be.
If light from a distant galaxy comes to Earth and it has gamma ray energies, then that explosion must have been incredibly powerful, because it turns out that as light travels through space, the wavelength of the light gets stretched out, and this stretching causes the light to lose energy. And since the light rays have traveled a very great distance through the cosmos to reach us, and they're still gamma rays, they must have started out with a great deal of energy.
And the amount of energies are unbelievable. You're talking about the entire energy budget of the sun over its whole lifetime, emitted over the course of just a few seconds. These are amazingly violent, amazingly powerful events.
In July 2008, NASA launches the Fermi Space Telescope. Its mission, to discover the source of these huge blasts.
What Fermi does is open our eyes to the universe that's there, but gives us such a different view that we really get a deeper and greater understanding of what's going on. If you had gamma ray eyes, the Milky Way would be blazingly bright across the center of the sky. Your vision would be dominated by these very dense pulsing stars and supermassive black holes.
And it's black holes that may solve the mystery of gamma ray bursts. When a truly gigantic star dies, one at least 25 times more massive than our own sun, it collapses to form a black hole. Scientists believe black holes are one of the few things in the universe large enough and powerful enough to generate gamma ray bursts.
Gamma ray bursts are the birth cries of black holes. When a massive star explodes and becomes a supernova, the core collapses and forms a black hole. Material falls around it, swirls into a huge disk. It gets incredibly hot. As it's falling into the black hole, it forms a tremendous magnetic field as well.
The remains of the star spiral towards the black hole, accelerating to close to the speed of light, heating to millions of degrees. Enormous electromagnetic forces fling some of this matter outwards, hurtling up and down along the black hole's huge magnetic fields. The matter collides with debris from the initial explosion. These high-speed collisions unleash unimaginable amounts of energy. This is the gamma ray burst.
Gamma ray bursts are fascinating. You can study them throughout the universe because they're so bright. But if you move them in really close to the Earth, let's say within 6,000 light years of the Earth, they become extremely destructive.
The beams are so huge that if a gamma ray burst occurs even closer to Earth, by the time it reaches the Earth, the beam will be wide enough to engulf our entire solar system.
Basically, if you were standing on the Earth and you looked up, you would see a flash of light. And before you could even say, "What's that?" you'd be gone. The amount of energy in the beam that travels across space is so intense, it would basically light the Earth on fire from that distance. It would strip off the Earth's atmosphere, it would boil the oceans, it would melt the rock, it would be apocalyptic beyond apocalyptic.
This is the worst-case scenario. But what if a gamma ray burst hit the Earth from further out? Would we survive?
People ask what would happen if there was a gamma ray burst within 6,000 light years of the Earth. It's actually not the right question. There have been gamma ray bursts that close to the Earth, and there probably have been extinctions of life on Earth due to gamma ray bursts.
200 million years after snowball Earth, the oceans are teeming with complex life. But 440 million years ago, 85% of all these creatures die. And the killer may have been a single devastating gamma ray burst. The blast penetrates the ocean's upper layers, killing the creatures that live near the surface. Creatures living further down survived the initial onslaught, but not for long, because the blast also damages the Earth's ozone layer, exposing the planet to the sun's deadly UV radiation, triggering acid rain and lowering global temperatures. Over 500,000 years, the creatures that survived the gamma ray burst get taken out by its after effects. If a gamma ray burst has wiped out life in the past, it could happen in the future. And astronomers think the next burst could come from a dangerously unstable star, WR104.
WR104 is the nightmare. We now have a potential candidate for what may become a gamma ray burster with our name on it. We are literally staring down the gun barrel of WR104.
It's not one, but two massive stars orbiting each other. The stars will die in a massive explosion, spawning a black hole and blasting out gamma rays.
The object is about 8,000 light years away, so we are within the kill radius of this object. So you could be doing your laundry tomorrow, look up in the sky, and all of a sudden there's this burst of radiation raining down from the heavens.
The radiation rips off the Earth's ozone layer, creating a toxic smog and exposing us to the sun's deadly rays.
Life as we know it could cease to exist. Plants would be scorched. Animals which depend upon plant life would then begin to die. Human civilization would have to go underground.
It may sound like the Death Star destroying the Earth in Star Wars, but the difference is the Death Star isn't going to happen. A gamma ray burst might.
Our extinction could happen at any time. And the fatal blow doesn't have to come from space. It could come from the very thing that makes life possible, the Earth itself.
Earth's defenses appear to be weakening. The spinning molten core of Earth generates a magnetic field that bursts from the poles, cocooning our entire planet in a blanket of magnetism. This invisible force field deflects deadly charged particles streaming from the sun, protecting us and our atmosphere from catastrophic damage. Now, scientists fear we might be losing this vital shield.
In the last about 200 years, it's weakened by about 10%. And if it continues at this rate, in a couple thousand years, it might go down to nothing.
If it were to disappear forever, we would be in trouble in the long run.
What will happen to Earth if we lose our magnetic protection? To find out, we only have to look at our planetary neighbor.
Mars may have once been like Earth with a thick atmosphere and water on its surface. That's gone. Why? Well, we know Mars doesn't have a very strong magnetic field, and that means it can't protect itself from the solar wind. These particles come streaming out of the sun and they hit Mars's atmosphere and blow it away.
Its atmosphere was actually stripped off by the solar wind because it didn't have a protective cocoon of a magnetic field. Today, if you look at Mars, it's cold, it's barren, it's lifeless because it doesn't have an atmosphere.
Is our planet really destined to lose its magnetic field and turn into a barren place like Mars? Geophysicist Dan Lathrop and his team have built a replica of the Earth's core to play out the evolution of magnetic fields in fast forward. Lathrop wants to know if the Earth's magnetic decline is part of a normal cycle of peaks and dips, or if it signals the beginning of a terminal decline.
Having an experiment like this allows you to get closer to something like a planetary core than could ever be done by any other means.
Liquid iron is too hot to handle, so Lathrop fills his 10-foot ball with the next best thing, 12.5 tons of liquid sodium metal.
When we run the experiment, the main thing that we're trying to understand is how the swirling mass of liquid sodium, this sort of turbulent, roiling flow of a liquid metal, generates electric currents and magnetic fields, and try to use that then to understand how planets' interiors do the same thing.
Lathrop starts the motor, spinning the ball, replicating how our planet rotates, but 350,000 times faster. Inside the spinning ball, the molten sodium starts to swirl. Charged particles race around the core.
Okay, yeah, that's good. It's coming into view.
A magnetic field emerges from the poles of the ball, and it looks just like the one that protects the Earth. Lathrop is measuring dips in the strength of the ball's magnetic field, but these dips recover and peak again. Lathrop has also witnessed the magnetic poles of his experiment wandering around. Amazingly, scientists find the Earth's poles do a similar thing.
As we look at the Earth's magnetic field, we can see that the direction the compasses are pointing toward is migrating to the north at a rate of several tens of miles per year. It's migrated off of Canada, is moving now towards Siberia. Will it keep going to Siberia and beyond that, or will it come back again and reach toward Canada? It's hard to predict what will happen.
To try and predict the future, scientists search for clues in our planet's magnetic past. Planetary scientist Janie Radabaugh is in Hawaii, home to Kilauea, the world's most active volcano, making it the perfect natural lab to study Earth's magnetic history.
The great thing about lava flows is that they trap the Earth's magnetic field inside of them and then freeze it in place. So now if we go and pick up the rocks from these lava flows, we can actually find out the orientation of the magnetic field in the past.
Lava contains particles of iron. When molten, these iron particles line up with the Earth's magnetic field. Then, as the lava cools, this orientation is locked in place. By digging down through layers of historic lava flows, scientists have revealed a magnetic record that stretches back for millions of years. And it shows the Earth's field doesn't just weaken and move. From time to time, the whole field flips. The North and South poles actually swap places.
The field was aligned in one direction for a while, and if you come up a little ways higher in that column of lava rock, we find it was actually oriented completely the opposite direction. 180 degrees from where it is today. It does that a number of times, dozens of times. So that tells us that the magnetic field of the Earth changes direction, not on kind of a regular basis, but once in a while, spaced by tens of thousands of years, maybe up to a couple of million years apart. And it flips from north to south, changing directions over the course of Earth's history.
How will the next magnetic somersault impact life on Earth? The surprising answer, very little. Biologists have dug deep into the Earth's fossil record and discovered that magnetic flips aren't cataclysmic.
What we do know is that it doesn't take so long that we're left unprotected for a long enough time that life is wiped out. We don't see mass extinction events around every magnetic field flipping event, and therefore we know it must be relatively fast.
The Earth's magnetic shield has protected life from the sun's radiation for billions of years, and it will continue to do so. But we are different than our ancient ancestors. We harness the force of electromagnetism in every device that powers our technology. And this puts us at risk from a threat that could bring the human race to its knees. Earth is the only planet in the solar system covered with oceans. Around 320 million cubic miles of them, drenching 70% of the planet's surface. Despite its abundance, the Earth's water baffles the experts because our planet's crust was born dry.
If you look at where the water is distributed in our solar system, there are no chunks of ice here in the inner solar system. So how did our planet Earth, so close to the sun, end up with so much water?
The water could have come from beyond the snow line, delivered by icy comets. But it would take tens of millions of impacts to fill the Earth's oceans.
Take a stroll today by the ocean and look out over that vast amount of water and think about that arriving in small chunks of ice here on the Earth. It's an incredible idea.
If comets did deliver the Earth's oceans, what could have caused so many of them to crash into our planet? Hidden inside the craters of the moon is a clue.
Right. Okay, I got a hydrogen. Yeah, pick up that little rock.
In the 1970s, Apollo astronauts collect rocks from the moon's largest craters to determine when they formed.
We brought them back to our laboratories and we could date them. When were those rocks actually made?
Planetary geologists had assumed these craters got blasted out around the time the moon was formed. They were in for a big surprise.
We found that many of the big impact basins on the moon were formed not in the earliest days of the accretion of the moon, but several hundred million years later, during a period we call the late heavy bombardment. Late because it happened several hundred million years after the Earth and moon had formed.
The late heavy bombardment kicks off when the gas giants align. Their combined gravity disrupts a vast belt of asteroids close to Mars, sending a shower of rocks towards Earth, the moon, and the other inner planets. Neptune swings outwards, smashing into the comets of the Kuiper Belt and sending many of them hurtling inward as well.
All hell breaks loose. 99% of the Kuiper Belt, the asteroid belt, disappear. Lots of bodies get thrown every which way. We look at the moon, we see that it is scarred, it is covered with craters.
The Earth didn't somehow magically escape that same bombardment. For every crater you see on the moon, the Earth is a bigger target out there in space. There are probably 20 or 30 craters formed on the Earth. We don't necessarily see them everywhere today because it's a lively planet with geologic processes that erase those craters.
The Earth is pummeled by the late heavy bombardment. But how many of these impacts come from water-rich comets?
We don't know. And that's one of the forefront science questions is, could the comets have come in to deliver ocean water at that time?
If comets did make our oceans, they should have left behind a unique chemical signature, because not all water is the same. On Earth, for every 10,000 drops of ordinary water, there exist 3 drops of semi-heavy water, a rare molecule made from deuterium instead of hydrogen.
Deuterium is a normal hydrogen nucleus, except instead of just being one proton by itself, it's a proton and a neutron connected together.
The extra neutron in deuterium adds weight, and that's why water made from these atoms is called heavy. Semi-heavy water forms more easily in cold conditions, so the edges of the solar system have more of it than regions closer to the sun.
The ratio of deuterium to hydrogen is a very sensitive probe of where water formed in our solar system. And therefore we can look at the abundance of heavy water to determine where that water formed and how.
In 1986, scientists get their first opportunity to test the chemistry of cometary water when Halley's Comet makes a fleeting return to the night sky. Astronomers look for the telltale signature of semi-heavy water, but the result is not what they're expecting.
They measured the water for the first time and found it was about twice as heavy as the Earth oceans.
Hyakutake and Hale-Bopp passed by in the 1990s. These recently seen comets are as old as the comets that smashed into the Earth during the late heavy bombardment. But Hyakutake and Hale-Bopp turn out to have way more semi-heavy water than the Earth's oceans.
People started to get worried because the entire Earth water budget, as measured by oceans, could not be made of just these comets.
In 2014, the Rosetta space probe measures a comet up close, and the results seal the deal. A semi-heavy water content 3 times greater than the water on Earth.
For the most part, the chemistry of Earth's oceans and atmospheres is actually a very poor match for the chemistry of comets.
When we look at the flavor of hydrogen in the water molecules that make up the comets that we've measured so far, it doesn't exactly match the flavor of the water that we find on our planet.
It's clear in my mind that comets could not have brought all of Earth's water.
If the dirty snowballs weren't to blame, what was? An unexpected candidate begins to emerge. In 2011, the Dawn space probe flies by the giant asteroid Vesta. We used to think rocky objects like Vesta were completely dry, but the observation team see evidence of water on the surface. And Vesta's water turns out to be a perfect chemical match to Earth's oceans.
The type of water is exactly what we think is contributing to the water on the Earth. So it looks like a really solid deal that those types of asteroids were putting the water on the Earth.
Scientists turn their focus from comets to asteroids. But how could these dry-looking rocks have provided enough water to fill the Earth's oceans? The explanation could lie within the haunting remains of a failed planet. Today, our solar system hosts 4 rocky planets: Mercury, Venus, Earth, and Mars. But there should have been 5.
Billions of years ago, planets were forming all over our solar system, but there was an area in between Mars and Jupiter where the gravity of Jupiter pretty much pulled apart anything that tried to form.
Today, the scattered remains of a failed rocky planet fill this gravitational battleground. Its debris forms a vast band of rubble around the Sun called the asteroid belt. Rocks inside the asteroid belt range in size from grains of sand to giant boulders hundreds of miles wide.
When I first started studying astronomy, we called them rocks, dry rocks. Now we understand that there may be a lot of water, maybe even liquid water, on some of the larger asteroids.
Our newfound understanding of asteroid water comes from a study of meteorites, tiny fragments from the asteroid belt that sometimes fall to Earth.
I've got a sample of a meteorite called a carbonaceous chondrite. And it looks and feels rather dry to the touch, but I can tell you that that sample actually contains about 20% by weight water.
Even crushing doesn't release the hidden moisture because the water is chemically bound to the materials that make up the rock.
And let's see if we can get some heat going here on our burner.
Heat allows the water molecules to break their chemical bonds and escape as vapor.
Look at all that water coming out. Just this small sample of meteorite is driving off all of this water. So here is direct, tangible evidence of the amount of water, the astonishing amount of water that can be delivered to the Earth from the impact of asteroids.
4 billion years ago, countless asteroids smash into the Earth during the late heavy bombardment. Each impact generates an intense burst of heat that releases the water trapped inside the asteroid. This water vapor then falls back to the ground as rain. And this same water still exists today in our oceans, our rivers, even in our coffee cups. The basic unit for life is the cell. To understand how it works, think of it like an industrial city. Tiny structures inside the cell work like factories. They take in raw materials and transform them into more complex forms, such as the hardware to build new cells. And just like a city, cells also need to produce power to keep their industrial units rolling. Some scientists believe that the key to the origin of life is hidden in the way life creates and uses energy.
It all comes down to energy. Energy is what drives complexity and development in technology. We see it in human history. It drove development and complexity in the story of life.
Today, cells have complex biological power stations built inside them. These structures help to drive chemical energy in and out of the cell membrane. And this chemical flow ultimately provides the cell with power. But the very first cells wouldn't have had the luxury of a complex system to generate its own chemical flow. And energy from the sun would have been too overpowering. Instead, scientists believe life must have gotten started in a shady spot with chemical energy already moving through it. In the 1970s, scientists embarked on a daring submarine mission to a long volcanic crack on the bottom of the Pacific Ocean. They were amazed to discover tall, chimney-like structures belching hot, volcanic water. And even more amazingly, these structures were covered with life.
What really blew people's minds when we first discovered these was the ecosystems, like oases of life, huddled around these black smokers miles deep in the water and the sea where the light of the sun never shines.
Before these vents were discovered, nobody knew that life could exist without light. But here were creatures thriving on chemical energy, jetting directly from the seabed. Scientists then began to wonder if the same chemical energy could have kick-started life. But there was a big problem.
These vents that were first discovered were really too hot to be a site for the origin of life.
Then, in the year 2000, scientists working 9 miles west of the Mid-Atlantic Ridge discovered a new, much cooler type of vent. They named them alkaline vents, after their unique chemistry.
What we find with these alkaline vents, we have this warm, mineral-rich water seeping out of the seabed and then kind of mixing and interacting with the cold seawater around it, is it deposits the solids and kind of builds up these vast chimney, kind of towering type structures.
The temperature inside the towers was perfect for organic molecules to assemble into more complicated forms. But did these curious structures also have the flow of energy needed to turn simple chemistry into biology? Laurie Barge is part of a NASA team that grows alkaline vents.
Now we're beginning to test in the lab what specifically could be happening on vents on the early Earth. We have to take into account the conditions of the early atmosphere, of the early ocean, the type of ocean crust and reactions that would have been occurring.
Laurie starts by injecting alkaline fluids into a simulation of an early Earth ocean.
The ocean here contains dissolved iron, as it would have on the early Earth, And then the chimney that you're seeing is the precipitate that forms when you have two contrasting solutions like this.
A delicate chimney builds up inside the flask. And because this structure is alkaline, it reacts with the acidic water around it, drawing chemical energy into the walls of the chimney. And this chemical flow is almost identical to the one generated by living cells today. But energy and temperature are not the only features these alkaline vents share with living cells.
The curious thing about these alkaline vents is that the pockets and the pores and the kind of channels and tunnels we find riddling their way throughout these structures, these chimneys, are about the same size as cells.
On the early Earth, these tiny pockets would have provided a warm crucible for the three basic building blocks of life to come together. Chemical energy flooding through the chimney walls may then have jump-started the tiny metabolic engines inside these protocells. After millions of years, the protocells could have developed a way to make energy for themselves, and then they could have broken free. For the first time in history, chemistry becomes life. Alkaline vents are the leading theory for the origin of life. But is it possible these simple cells faced competition from another life form? A more advanced cell that arrived on the Earth fully fledged from another planet? Is it possible that our ancestors were aliens?